So in chemistry, when we need to measure things, we need to count really, really small things, and we can't do that um, because atoms are too small to count. So what happens is we have to figure out an alternative way to count. So just a really quick story. When I was a kid, your age, I lived on a farm, and we purchased corn all the time. So I had a wagon and a tractor, and I'd be connected to the wagon, and we'd take the wagon into town. This is the steering wheel. This is me sitting on the tractor, and I was a good-looking young man back then. So we would go to school, or I'd go to school. We'd go to town. I'd go to town with my wagon, and I'd be driving over, and there's a scale in the town. And I'd pull the wagon onto the scale. So the wagon would be sitting here on the scale. The wagon shrunk a little bit on the way to town. But anyway, it was sitting on the scale, and we'd weigh the wagon. Then we'd fill the wagon with corn, and then we'd come back on the scale with a full wagon load of corn. And this is corn. And we would then get a weight. And the weight was somewhere around, usually around 14,000 pounds. Then we would divide that by 56. And then whatever that equaled, let's just go ahead and do that. So 14,000 divided by 56 is 250. All right, so that would be, the reason we divide it is because there's this many pounds per bushel. Now I'm going to set that up a slightly different way and see if it looks familiar to you. So we would say we have 14,000 pounds, but I want to know how many bushels in that pounds. Oh, by the way, I'm assuming that everybody knows that corn weighs 56 pounds a bushel. Actually, I'm just teasing. I didn't expect you to know that. But one bushel of corn does have a weight of 56 pounds, and we're agreed on that in the industry. So when you buy corn or sell corns, you can find out how many bushels you have by dividing by 56. So if we know that one bushel weighs 56 pounds and I want to get rid of pounds, wouldn't I be able to put pounds on the bottom and bushels on the top, just like we just completed? Okay, so we know that one bushel is 56 pounds. So 14,000 times 1, then divide by 56, and it's 250 bushel. All right, so the point I'm trying to make is that in rural communities and in lots of other communities, we measure things by using their weights. So if we divide this by the agreed upon weight of a bushel, we know we have 250 bushels. All right. We did the same thing with soybeans, except we'd fill the wagon first with soybeans and take them to town and weigh it, and then unload it and weigh it empty again, and we'd sell them. And for soybeans, one bushel is 60 pounds. And so there's an agreed upon standard that one bushel is 60 pounds. So we'd have our 14,000 pounds, and we'd multiply by a bushel over 60 pounds. And so that would be my finger's too fat. Divided by 60 equals, there we go. So 233. Because soybeans have a different density than corn. So then we'd pay about somewhere between $3 and $4 a bushel. So it would be somewhere between $750 and $1,000 for that wagon of corn. And over here we'd sell it for about $6 a bushel, so it'd be about $1,200 for the soybeans. But that's how the farmers buy and sell stuff, is based on the weight of bushels. And you may have heard of a bushel before, like a bushel basket or a bushel of apples. All right, so I'm going to pause for just a second. Is there any question about what I just did, specifically understanding what this means. So if I had 14,000 pounds, I know that a bushel is 56 pounds. That'd be 250 bushels. So give me some feedback. Are you still with me and awake? Chat window. Is this making what I just did? Does that make sense? Scale of 1 to 10. I hear some yes, 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 yes. Okay, so I got a few people with me, I know. All right, so about an 8. Good, and yes, good. All right, so let's see if we can apply it to the mole concept. So I'm going to give you, and you might want to jot down a couple of notes about this. So in chemistry, we use something called moles. So 1 mole is, okay, it is 6.02 times 10 to the 23rd pieces. So a mole is that many pieces. That's a big, big number. But it's just a number. So if I said to you, how many donuts are in a mole of, or in a dozen donuts, you'd say there are 12. Y'all agree with that? If I said how many bottles of soda are in a 6-pack, you'd say 6. If I said how many shoes are in a pair of shoes, you'd say 2. If I said how many bottle rockets are in a gross of bottle rockets, you'd say 12 dozen, or 144. If I said how many sodas are in a case of soda, that used to be defined, but now it's a little different, but usually it used to be 24 all the time. So my point is that this word just means a number. So a mole is this number. Now it's a huge number. If I had a mole of donuts, the world would be covered with donuts about 5 miles deep probably. So it's a huge number, but it's still just a number. All right, but since atoms are so small, and because if we started counting and counted for the rest of our lives, day and night, at the rate of 1, 2, 3, 4, 5, 6, we would never even get anywhere close. We'd be dead before we'll die before we get to this number. And that includes both you and me. And I'm closer to the end of life than you guys are, but the point is, it's a huge number and you can't count that far. So what we have to do is come up with an alternative way, but guess what? How do we count our corn? We counted it by using weights. And we can also count in chemistry by using weights. And I've been trying to teach you that sort of a backdoor approach, but I didn't tell you what it was called, but we've been calculating formula weights. Remember on the strange names assignment? And then on last class we had an assignment where we're calculating formula weights. So if you put that formula weight in grams, that is 1 mole. So the GFW stands for gram formula weight. Gram formula weight. So a quick example, if I wanted to find the gram formula weight of sodium hydroxide, we would find the weight of sodium. And now I'm going to just tell you what these are, but I am looking on the periodic table in my head. Those are the masses like we've been looking up on the periodic table for the different elements. So sodium's 23, oxygen's 16, hydrogen's 1. If you add them together, you get 40. All right, so if I say 40 grams, that's 1 mole. Now if I did water, in water I've got hydrogen is 1, but it's times 2, and that's 16. That's just one of those. So that would be 18 grams equals 1 mole. Now it has a different weight because it's a different thing, just like up here, the corn and the soybeans had different weights because they're different things. So they have different weights for the same amount of pieces. And in this case, it was the different weight is for the same volume, but here it's a different weight for the same number of pieces. So what that means is sodium hydroxide, if I have 40 grams of it, I have this many pieces of sodium hydroxide. If I have 18 grams of water, I have this many pieces of water. The number of pieces is the same, but the masses are different. All right. Give me, you understand how that the gram formula weight is the sum of the formula masses that you find on the periodic table. So can you guys give me some feedback in the chat window real quick? Do you understand that concept? The gram formula weight is the formula mass that we've been calculating in class. Feedback window in the chat window. All right, somebody else? Okay, good. Good. All right, so let's try and do a sample problem now. I'll use these two numbers. So let's suppose I had 15 grams of sodium hydroxide, and I wanted to change it to moles. Well, I could say 15 grams of NaOH. I want to cancel grams of NaOH. So where would I write them? Would I put them on the top or on the bottom? Yeah, you put them on the bottom. So I would say grams of NaOH down here, just like we were working on earlier today. We'd have moles of NaOH up here. And for this part of my class, if you get confused, you can remember that 1 always goes with moles. And it's going to go with moles all the way through the mole unit that we're working on right now. It changes a little bit when we get to stoichiometry, but right now, 1 always going to go with moles. And then we said the weight was 40 grams. So now we have 15 times 1, then divide by 40. So 15 divided by 40 equals 0.375 moles of NaOH. All right, are we cool? So if I had a glass of water, so suppose I have this cup full of water, and we'll say that it's 400 milliliters of water, which is about 400 grams. Now it's probably not big enough to hold 400. We'll say it's 250 grams of water. And we're going to change that to moles. So I'd say grams of water be on the bottom, moles of water on top, and 1 goes with moles, and the number of grams in a mole of water was 18. Remember, we calculated that a minute ago, so it'd be 18. So now I'd have 250 times 1, remember that's over 1, so 250 over 18. Grams of water cancel, and the unit's going to be moles, and 250 divided by 18 is 13.9. All right, so 13.888, I rounded off to 13.9. So you'd have 13.9 moles of water if this cup was full of water. I always like this cup. All right, so that's how you change grams to moles. If you want to change moles to grams, if I took my 13.9 moles of water, this time you want to change moles back to grams, so if you want to cancel moles, so moles go on the bottom. Grams will go on the top. 1 goes to moles, that's 18 grams, because we calculated it earlier, like here. But this time, you multiply 13.9 times 18. Whoops, 13.9 times 18. And I'm guessing it's going to be really close to 250, but I did round a little bit. There you go. So if you round that out, 250 grams of water. So what I've just shown you is how to change grams to moles and moles to grams. And that's all we're going to do on the next assignment that I'm going to post in Google Classroom. So I'm getting ready to post that now. And this one is a link. It's a web link. Now on this one, I want you to write them on paper and then submit a photo of the paper. So I won't be able to come in to Google Classroom and look at your papers like I did last time. So what I'm going to do is put you in breakout rooms again, and I'll try and drop in and see if you have questions. If I find that a bunch of people have questions, then I'll probably bring you back together, or bring 2 or 3 of you together in the same breakout room, which we can do that. And I think you can move from room to room too. All right. So I just assigned it. It's called Mole Conversions 1 in Google Classroom. Mole Conversions 1 in Google Classroom. And I'm going to do an example problem. Because this is what the assignment is going to look like. So I just go down toward the bottom here. Okay, so look at number 5. A chemist needs 3 moles of aluminum oxide for a particular experiment. How many grams? So you have 3 moles of aluminum oxide. Is how many grams? So I'm going to work that out on my paper now. So pen my paper again. All right, so aluminum oxide, it's Al2O3. So aluminum has a weight of 27. Now, where do you find that 27? Remember the masses on the periodic table. Oxygen has a mass of 16. But there are 2 atoms of aluminum, so you have to multiply by 2. There are 3 atoms of oxygen, so you multiply that by 3. So 27 times 2 is 54. 16 times 3 is 48. So now you add those 2 together. 54 plus 48 equals 102 grams. So 1 mole of aluminum oxide is 102 grams. So that's nothing new. We've been doing that. So we want to do the conversion now to change to grams. So we would say 3 moles of aluminum oxide times, we want moles of aluminum oxide on the bottom because we want to cancel them like we just learned earlier today. We have grams of aluminum oxide on the top. We know that 1 goes with moles. We just calculated that there are 102 grams in 1 mole, so we'd have 306 grams of aluminum oxide. So if you wanted to find mass out a mole of aluminum oxide, you go back to the stock bottle, remember that's over 1, and you would measure out 306 grams, and that would be 3 moles. All right, remember that whatever's here cancels what's down there. So those 2 things cancel out. My final unit's grams. Okay. Now, I need to know if there are questions, but I don't know if you want to say, I got questions in front of everybody. So I think what I'll do is put you into breakout rooms. And we have about 35 minutes left of official time. And I'm going to try and move around from room to room for these next 35 minutes and see if you need help. And I would want to know if I could do another one. So yeah, we could do another one. So that was one of the 12. And I think everybody's questions on this will always be the same. So let me go back to that window and I'll share a screen again and we'll do one more. Okay, you should be able to see them there. So let's do number 6. So number 6 says, how many moles of water are in 360 grams of water? How many moles in 360 grams of water? So what you would do, can you guys, I'm wondering if you can still see the window. If you had my paper pen, can you still see it on the side well enough to read when I'm writing? Maybe say something if you can, yes or no, somebody. So I didn't hear anything, so I'm going to assume that you can't see it. So we're going to stop. All right, so that question was 360 grams. You want to know how many moles that is. So you write down what you're given, 360 grams of water. We know that we need to get rid of our grams of water, so we put it on the bottom. There's a rule that you'll find it always applies. Whatever you want to get rid of goes opposite. So if you have grams of water written on the first line, then remember that's always like over 1. So you put grams of water on the bottom of your conversion factor. If you had grams of water on the bottom of this ratio, for example, then you would put it on the top. So you put it opposite. Most of the time right now it's going to be always on the bottom. Okay, so up here you're going to put moles of water because that's what you're trying to find right here. And we said that 1 always goes with moles. Earlier we calculated the mass of water was 18 grams. So I have 360 divided by 18. So it's 360 times 1. Remember, you multiply the numbers across the top. 1 times 18 is 18. So 360 divided by 18. You get your calculator out. I think it's going to be 20. But in case you don't like doing them in your head, 360 divided by 18. All right, so that's 20. In terms of units, since grams are on top and on the bottom, they cancel, so my unit is moles. All right, so now the way I want the work shown when you turn it in, I'm going to want them looking like this. If you want, you don't have to write this step in. So if you do this, it's sufficient. Here, this time I wrote the numbers in, but you don't have to write those in when you turn it in. You can if you want to, but you don't need to. But I want a photo of work that looks like this for all 12 problems. The way I got 18 is like this. I know that water is H2O, so I look on a periodic table. I'll show you real quick. It's coming. Okay, so if you go to hydrogen, right here, see hydrogen has a mass of 1, the bottom number there. On the other side, oxygen has a mass of 16. See right here, 16. So what I did was take the 1 from hydrogen, multiply it by 2, take the 16 from oxygen. There's only 1 atom of oxygen, so it's times 1. So 1 times 2 is 2, plus 16 times 1 is 18, and that's how I got the 18. All right, so 18 grams is 1 mole. So to find the mass in 1 mole, I've already taught you how to do that, because if you go back to the assignment, show you again, if we go back to old work that we've been doing, remember the formulas and formula masses? So not everybody has this done, obviously, but when you do something like this, if we do, remember how we did these and we unchecked acids? This is old homework from last class, and we want just chemical names here. And it generates a quiz for us. So we have magnesium fluoride. So MgF2. So you get that based on the charges, because magnesium is plus 2 and fluorine's minus 1. And then when we added them up, we took the weight of magnesium plus the weight of 2 fluorines. So it'd be 24 plus 19 times 2. Now where do I got these numbers from the periodic table like I just showed you. So magnesium is 24.3, just rounded off to 24. If you do, let's see if there's a harder one here. There's not really one. None of these are very difficult. Barium phosphide, you'd have Ba3P2 when you can think about charges. Then you have the weight of barium times 3 plus the weight of phosphorus times 2. All right, so 24 plus 19 times 2, what is that? 30, 24 and 38, so it'd be 58, 62. Okay, then you're supposed to do 25 of these, and that gives you practice on really finding molar mass. Okay, any questions for the large group?